Alright guys, in this section we're going to be discussing one of the most powerful differentiation rules, the chain rule. This rule is going to deal with composite functions. When we have a function within a function, if you recall from your algebra course, we can compose more than two functions at a time, right? We can have function within a function and keep going that way. Well, this rule, the chain rule, is going to allow us to differentiate this type of functions, composite functions, and not only that, but it will also save us some time differentiating other functions that would have taken us a long time with our basic differentiation rules. So this is how a composite function looks like, right? If you recall from your pre-calculus course, you have a function f, and inside a function you're going to evaluate g of x, right? Some other function g, and our input is x here. Now, if we replace this g of x with some u, and let's say here u is just this function g of x, and think of the input of f as the output of g, then we can describe this f as the outer function and this g as the inner function. Again, this g for us is also this u. If you want to find the derivative of y with respect of x, using Leibniz notation here, looking at this function here, this form of the function, f of u, right, you will have to find the rate at which f is changing with respect of u. But since we want to find this with respect of x, you would need to multiply by the derivative of the inside function, in this case g of x. Now, okay, another way of saying this is dy du times du dx would be equal to my derivative of y with respect of x, because y is just this f of u. So you have it here. F of u is really just your y there. Okay, so this is the idea of the chain rule. When you have a composite function, and we have the example of composition of two functions here, but this rule will also work for more than two functions nested together. So if you keep having a function within a function, you have to use this rule more than one time. But if you think of this function y as a function of x here, and you wanted to remember, think of the derivative as rate of change, right? How fast it's going. So another way of interpreting this rule would be if dy du is how fast y is changing with respect to u, and du and dx is how fast u is changing with respect of x, and remember u is really g of x, then the rate of change for y with respect of x, so dy dx, would be the product of the two. Okay, so here we have our chain rule, and we have the two notations here. So this is our Leibniz notation. We had dy du times du dx, and again, u is our inner function here, is this g of x. Or we can also write it with the Newton's notation. F of g of x, the derivative of that composite function, would be equal to the derivative of the outside function times the derivative of the inside function. Okay, so here we have an example. Y equals 2x minus 5 quantity cube. The first thing you want to do before applying the chain rule is identify the inner function and the outer function, right? So because once we have that, we'll be able to find their derivatives and multiply them and go from there. Here, so this is a pretty straightforward example. You have a cubic, or you have this linear function here inside of a cubic. I'm going to work this one out step by step so you see exactly what's going on, but eventually you just identify those functions, you can skip those steps. Okay, so from our notation above, I've even used the same colors here so you can identify what we're doing. The inner function would be this linear function inside this cubic. So if I let this f be x cubed, that would be the outer function here, and the g in blue would be our linear function. When you compose f with g, you would get this y right here, function of interest here. So now that you've identified the inner and outer function, we can go ahead and apply the chain rule. So dy dx is going to be equal to the derivative of the outer function. So remember, this instead of x is going to be this whole thing here. So what is the derivative of x cubed? Well, we know that's the power. We're going to use our power rule, and that's going to be bring the 3 to the front, and 2x minus 5, the inside stays the same, and that power goes down 1 degree, right? Or the power goes down by 1. All right, next we're going to multiply by the derivative of the inside function. So we're going to multiply the derivative of 2x minus 5. We know how to do that by doing our power rule, and derivative of a constant is 0. So derivative of 2x is just 2, and that is it, because the derivative of negative 5 is just 0. So we end up with this, and then now we can simplify. Always simplify your final expression to try to give the most simplified expression at the end. So this 2 can multiply the 3, we get 6, and there's no need to expand that binomial. We just leave it as 2x minus 5 squared. So there it is. This is our derivative of y. Okay, so here's another example. We have y equals 6 over x cubed minus 2 quantity cubed. So this is an example of how the chain rule is really going to save us some time here. We know that we could use, from the previous section, we could use the quotient rule, since this is a quotient, to find the derivative of this function here. But chain rule is going to allow us to do this in a relatively faster way here than if we had done the quotient rule. So you can do this when you have a constant on top. So if you have a constant on the numerator, then we can rewrite this function in the following way. 6, we can bring the denominator to the top, x cubed minus 2, raised to the negative 3 now, and change that exponent to negative 3. Doing that would allow us to do now the power rule combined with chain rule. So that hopefully you can see now that our inner function here is going to be the inside of what's in this parenthesis. So then dy dx will be equal to the derivative of the outer function. And this 6, by the way, guys, is just a constant in front. So we know that our constant multiple rule says I can just leave that outside. Then do the derivative of the outer function, which will bring the negative 3 to the front. And this goes down. Negative 3 minus 1, so I give you a minus 4. Okay, so that's the derivative of the outer function right there. Okay, now we still need to multiply by the derivative of the inside, and the derivative of the inside is just the derivative of x cubed minus 2. So we know how to do that. Derivative of x cubed is going to be 3x squared, and the derivative of the constant just goes, so it's just 0. So that is it. Now the rest is just simplifying what we have here. Let's go ahead and clean this up. We could combine this 6 with the negative 3 and the 3 here into a 6 times 3 is 18 times 3 is 54. So we get negative 54. Remember, we still have the x squared times x cubed minus 2 all over raised to the negative 4. Now, you can always bring this whole expression x cubed minus 2 to the bottom and change that negative exponent to a positive exponent. There's no need to expand the bottom here. This would be the simplest form. And here we have it. That's our answer. Okay, guys, so another example here, similar to the previous one, but now with a radical as well. So we have the quotient. We can use a similar idea than the last before, but we need to deal with that radical as well. So any radical that you encounter in a function can be written as a fractional exponent, right? So then that's what we're going to do. We're going to take that 1 over, and instead of having the square root of 3x plus 5, we're going to have 3x plus 5 raised to the 1/2. So that's equivalent to that square root. And then we're going to use or do what we did on the previous example, bring this to the top. Since I have a constant on the numerator and it's just a 1, I can just bring the 3x plus 5 to the top and change the sign of the exponent. So we end up with that. Notice how we haven't started on the derivative yet. This is just rewriting this function y so that we can use our basic differentiation rules combined together with the chain rule. So now we're ready to find dy dx. Dy dx will be equal to, from here, from this last expression, you can see how the inner function is whatever's inside the parentheses, and the outer function is just, x raised to the negative 1/2, that power function. So then we're going to use power rule first, because remember, we always do the outer function here, the derivative of the outer function first. So that's going to be bring the negative 1/2 to the front, keep the inside the same, everything is the same there, and that negative 1/2 goes down 1 to So negative 1/2 minus 1 would be negative 3/2, and then times the derivative of the inside. And that's really easy. That's just derivative of 3x is just 3, derivative of 5 is just 0, so it's just a nice 3 there. Of course, we will simplify this. We've got the derivative already. That is the derivative. We need to simplify it a little bit. So this 3 combines with the negative 1/2 into 3, negative 3/2. And I have this 3x plus 5 raised to the negative 3/2, which we could also write it this way. 3 over 2 square root of 3x plus 5 cubed. Okay, so here we have our transcendental functions. The rules for the derivatives of those transcendental functions are generalized now with the chain rule. Instead of having just x as an input, we have some function u of x, right? So everything is going to work the same, but with chain rule, you're going to have to differentiate the inside, which is this u, multiply it to the derivative of the outer function, right? So that, for instance, we know already from previous sections this derivative of sine is cosine, right? But if we have derivative of sine of some function of x, then chain rule says we have to multiply by the derivative of the inside function of that u. Everything is going to work the same for all the other rules. Also our natural exponential rule here, the derivative e to the x is e to the x. But if we have e to the some function of x, then it's going to be the same. The same rule applies, but then chain rule says you multiply by the derivative of the inside function. So let's do an example with that one. Okay, so here if I have y equals e to the 5x, not e to the x, but e to the 5x, so here's where we're going to use our regular rule, but now generalized with chain rule is going to work in the following way. So notice how this e is the outer function and this 5x is the inner function. So you have to do the derivative of the outside first, which would be e to the whatever that was, the input. This doesn't change. And then chain rule says times the derivative of the inside, which is the 5x. So the derivative of 5x is just 5. And you can clean this up, but put the 5 in front, then you're done. So notice how chain rule is going to be now on just about every problem that we see. Every derivative that we compute, we're going to have to think about chain rule in order to get the correct answer. Okay, so here we have a new rule to add to our bank of differentiation rules, and that is the derivative of the natural log of x. And it's a very simple rule, and now that we know how to apply chain rule, we can actually prove this by starting with the function y equals ln x, right? So we're going to have, say we have y equals ln x. You know that from algebra that you can rewrite this logarithmic expression as exponential by doing the base of this log is e. So this is equivalent of saying e to the y is equal to x. And of course this rule is only going to work for x greater than 0 because that's the only domain where the logarithm makes sense. Okay, well if we have e to the y equal to x and we take the derivative with respect of x on both sides, then we're going to have on the left side we're going to have d of e to the y dx equal to dx dx. Now, here's where chain rule plays a big part in proving this rule. On the right side, dx dx is just 1, right? What's the derivative of x with respect of x? That's just 1. On the left side, you're going to apply chain rule because we're differentiating with respect of x, but this is e to the y, and y itself is a function of x. Remember what y is from right here. So then we're doing this example all over again, right? We're going to do the derivative of the outside, which is e to the y, times the derivative of the inside, which is y itself. And since that's a function of x, that's dy dx. Now, solving for dy dx here, we're going to get that dy dx is equal to 1 over e to the y. And if you remember what y is, we can rewrite this as e to the y is ln x. And e to the ln x is just x, right? Because e with ln are inverses of each other. They cancel each other out, and we get just 1 over x. And here we have it. The our rule for the derivative of natural log of x is equal to 1 over x. And again, this only works for x being greater than 0, since that's the only places where the log makes sense. Okay, so now we have not only the derivative of e to the x, we also have the derivative ln x. And just like we have these generalizations with the chain rule, now we can also generalize our new rule here. So derivative of ln of some u being a function of x, is going to be equal to derivative of the outside function, 1 over u, and then du dx, because we have to multiply by the derivative of the inside. Another way of saying this would be u prime over u. Remember, du dx is u prime, so derivative of u with respect of x, and this is also for x greater than 0. All right, well, now you may ask, well, I know what the derivative of e dx is, what the derivative of ln of x is, but what about if we have an exponential or a logarithmic function with a different base, different from e? In that case, chain rule is also going to help us derive those rules. Okay, so here if we have a to the x, and instead of e to the x, we have a to the x for a some other base. I can rewrite this expression, this exponential expression, as e to the ln of a, all that raised to the x. Since this e and the log, natural log, cancel each other out, this is equivalent as a, and then all that raised to the x. Now, ln of a is just a constant here, right? Because a is a constant, so ln of a is a constant. So the rule of exponents say I can multiply those exponents and have this equal to e to the ln a times x. So now, if I want to find the derivative with respect of x of this a to the x, that's equivalent of finding the derivative of this e to the ln a times x. And here's where chain rule is going to come in again in handy. We again have the derivative of e to something here. And ln a, remember, is just a constant, so this might as well be like this 5 right here, right? 5x, that's what we have here. E raised to the something x. So then if we do the derivative of this, this should be equal to e to the same thing, ln a times x. But then chain rule says times the derivative of the inside, in other words, this exponent. So derivative of this exponent is just ln a, because remember, this is the constant, that's just x, derivative of x is just 1, so then you end up with just ln of a. Now, simplifying this, or putting it back to the regular form here, remember this whole thing right there was just a to the x. That's right, this is a to the x times ln a, which we can also write the other way around if we'd like. Ln a times a to the x, either way. So that's our derivative now of an exponential function with any base. Similarly, for a logarithm of a different base other than e, we could use, if you remember, change of bases. This log base a of x is equivalent to ln of x over ln of a. Then I can rewrite this as 1 over ln of a, because ln of a, again, a is a constant, right? So that's just a number. This is constant times ln x. So if I take the derivative of this log function base a of x, that's equivalent as taking the derivative to this whole thing right here. All right, well, that we can do. This is just a constant here, so that just stays out, ln a. And then derivative of ln x, we just derived that previously. You already know what that is. That's 1 over x. So our final here answer would be 1 over x ln a. That's our derivative of a logarithm with any base here. Okay guys, so let me do one more example here where we may have to use chain rule a couple times here. So we have this function y equals ln natural log of square root of x squared minus 4. So again, you want to be able to identify the inner functions, right, and the outer function, and maybe more if we have more functions nested within each other. So I see that my outer function here is going to be, and I'm going to write this, y equals, my outer function is ln of whatever is inside there. Now, my inner function is whatever is inside this parenthesis of ln x. But notice how I have another function within the function. So we have the square root of something, but that something itself is not just x, it's x squared minus 4, so that itself is a function within the square root function, which is inside the natural log function. So we have 3 functions here nested within each other, right, composed with each other. So the rule is going to work the same, you just have to work your way in, right? So then we're going to start with the natural log, so dy dx is going to be equal to, what is the derivative of the natural log? It's 1 over the input, 1 over x. Now remember, your input is this whole thing inside the parentheses. So you're never going to change the input there for any given function. So we're going to have 1 over the square root of x squared minus 4. So we have that. And then times the derivative of the inside function. You can write this function as ln x of, instead of the square root, you can have it raised to the 1/2. And the inner function is still x squared minus 4. So the only reason we rewrote this like that is so that we can use the power rule in this next one here. So this would be times, now we're going to use the power rule, 1/2 x squared minus 4. And remember, we subtract 1 from the 1/2, so that gives us negative 1/2. So that's our second one there. And we don't stop there because we still have a function within that function, namely x squared minus 4. So then we need to multiply by the derivative of that inner function, which is derivative of x squared is 2x, and then the derivative of negative 4 is just 0, so it's just 2x then. All right, so finally we have now the derivative of y with respect of x here, and then what's left for us to do here is simplify. Notice how this 2 goes away with that 2, and I can bring this to the bottom here. So I have an x on the top. I have the square root of x squared minus 4 times the square root of x squared minus 4. This term right here in blue, because the exponent is negative, that can come down to the denominator, and the 1/2 exponent is really the square root. Notice how these two are the same. You can combine them into 1 and the root will go away. So the final answer would be x over x squared minus 4. This is our final answer for the derivative of this function. So in the same way, if you have several functions nested together, one within the other one, this chain rule is going to apply until you can't go any further here. So for instance, here x squared minus 4 was our stopping point because after this, we just have x. And once we get to x, we stop. So here's an example of how the chain rule gets applied twice in the same problem. But if you have more functions nested together, one within the other one, you need to apply the chain rule as many times as needed. Now, not only the chain rule applies to this rule, all the rules, the basic rules that we've seen, but also it would also generalize our product and quotient rule from the previous section. So make sure that you go back to those rules and generalize them with the chain rule. So here's a summary of all the differentiation rules that we've seen so far, and they've already been generalized with the chain rule. So remember, if we have composition of functions on any of these rules, then we have to apply chain rule to all of these. So notice how our constant multiple rule, our power rule, and the product rule, the quotient rule. Okay, so here we have a summary of all the differentiation rules that we've seen so far. And notice how some of these have simple in front of it as opposed to general. So that distinguishes the original rule from the one generalized with the chain rule. So notice how our power rule, the simple one, applies only for x raised to some power, and the general power rule applies to any function of x raised to a power. So then everything is going to work the same. It's going to have the same procedure, but now with the chain rule applied to it. So all of these functions here, and again, you can take any of these rules here, and we've already done that with some of these, and change that x with a function of x, right? Which typically we call the u here, but it could be anything. So don't get fixated on the letters, on the particular variable, but try to learn this, memorize these rules in words so that you understand that this x really just represents an input. And just like we have x, we could have something else, or we could have a function of x. And in that case, we have a composition. When we have a composition of functions, then you always have to think about chain rule and apply these rules with chain rule on top of that.